Okay, so basically, two classes of steel: plain carbon steels and alloy steels. Right? You should know the basic iron phase diagram, right? And the interstitial behavior in iron, right? So where right, that the relative size of the tetrahedral and octahedral sites in FCC and BCC iron, right? And that in austenite, interstitial atoms are going to reside on the larger octahedral sites, right? But that even in BCC, the tetrahedral sites are larger. They still end up staying. It still ends up staying in the octahedral sites because the asymmetry of the octahedral sites. So you only need to displace two atoms rather than the four neighboring atoms, right? And that this is basically what makes steel work, right? So the fact that the carbon, right, is also because of the mobility, the interstitial, the mobility of moving around from interstitial site to interstitial site are going to tend to align themselves with dislocation, right? Because they're the octahedral, if the carbon atom or the nitrogen atom is in the dislocation core and ends up being a low energy elastic configuration, right? And basically, remember, this is a tetragonal distortion, right? So this becomes a strong obstacle to dislocation motions, right? Dislocation motion, and that gives rise to the upper yield point phenomena and Luther's band, right? You go up until there's enough stress to break the dislocations free from their preferential carbon, right? The carbons are preferentially aligned along the dislocation. So you have to go up to a higher stress, but then once you break them away, you exceed the chiral stress for dislocation motion in general, right? Without all those pinning carbons. And so you have a lower yield point, right? And you get this Luther's band formation because you have a balance between moving dislocations in a new region and basically work hardening in the region back here. You get a little bit of deformation, you get a little bit of work hardening, and then it balances, and so then you get this band, Luther's band, that propagates. Right? It's also the same thing that's responsible for dynamic strain aging. Right? If you deform it, the right temperature range, it's slow enough, the interstitials catch up with the dislocations and repeatedly pin them. Right? So you get this oscillatory strain behavior. Right? At high enough temperatures, the deformation's easier, right? Because in BCC you activate a whole bunch more different slip systems, right? Preferentially a lot more. At lower temperatures, you don't quite have the mobility for the carbons, for the interstitials to catch up. So it's really just in this intermediate range. What we call that dynamic strain agent. Right? You also still have solid solution strengthening. Iron, because of its BCC nature, you have a very strong Hall-Petch effect, much stronger than aluminum. So grain size in steel is very important, and it's largely independent of temperature. Right? know the basics of the iron-carbon phase diagram, right? You don't necessarily need to know the exact temperature, right? But you should know that the eutectoid temperature is going to be about 730, right? Depending on the exact alloy composition, right? And the eutectic is slightly to the left of 1 weight % carbon, right?
Eutectoid.
The eutectoid, sorry. Right? So the eutectoid, the eutectic is a little different. The eutectoid is going to be slightly to the left of 1 weight % carbon, right? Know your basic rough range of critical temperatures, right? And right. And this chart here, right? Know what are the main morphologies of ferrite, the main microstructural features that we spent a lot of time going through each one in detail, right? And sort of be able to rank them as reconstructive and displacive, and know when each one's going to appear, right? And also this concept of paranucleation or para-equilibrium nucleation comes up over and over again as we go through, right? That we're at temperatures where the carbon has really fast mobility, right? The carbon can diffuse easily, right, interstitials, but the substitutional solid atoms, so the alloying elements, right, are not going to be able to partition at the same time scale as the transformation, right? So that means either they're going to slow down, right? They have to move by diffusion, longer range diffusion, right? Whereas interstitial diffusion is much faster than, right? We don't need vacancies for this to occur, right? And then we sort of just went through the major classes here, right? The major classifications of steels, all this stuff, not really super important, right? This is just more for your reference of being able to look things up. In terms of growth of ferrite, right? Okay, so the paratectic transformation, right, doesn't cause a major effect on the resulting microstructure, right? Because no matter what composition would come through the paratectic point, you still have to go through the whole austenite phase field. So depending on where we are, we may get some coring or other inhomogeneities in terms of composition, right? But generally, we're not too worried about that, right? Don't worry about cast irons, right? You should definitely, right, be able to make a sketch and describe what's going to happen for slow-cooled hypo, hyper, and eutectoid steels, right? That whether you're going to have pro-eutectoid ferrite or pro-eutectoid cementite, and where it's going to form, and generally what the microstructures look like, right? Yeah.
So I noticed that both ferrite and cementite form green boundary, but their morphology is different. Why is ferrite more like a?
Well, so they're different. I mean, ferrite is metallic, right? And the cementite is a ceramic material, right? It's intermetallic, right? So their chemistry is quite different. Their surface energy with respect to the austenite is going to be quite different, right? And the cementite interface tends to be higher, right? The cementite will spheridize at longer temperatures, right? You can give the spheridization heat treatment, right? But it involves quite a bit more complexity in terms of diffusional mechanisms rather than just partitioning carbon out, right, for growing pro-eutectoid ferrite. Right? It's not a complete answer, but it's right. They're just different things. So
are both of these images slow cooled?
yes. So this is slow cooled, right? And that so Kurgyumov-Sachs orientation relationship keeps coming up. You should know sort of what it is. And everyone should have gone through the exercise of drawing the Kurgyumov-Sachs relationship, right? And have an understanding of sort of where the atoms are, right? And that the key idea here is, right? So Kurgyumov-Sachs, we have got the 1-1-1 plane, right? So that's our close packed plane along a close packed direction in in FCC, right? And then in BCC, we don't have a close packed plane, but we do have close packed directions, right? So the Kurgyumov-Sachs aligns the close packed directions in both crystals, right? It also aligns the primary slip systems in both crystal systems, right? So sort of having an understanding of this orientation relationship is important, right? And then right, idiomorphic and allotromorphic ferrite. Right? The basic where they show up, right? That they're going to be right, and then you don't necessarily need to derive it, but remember we have parabolic growth of the ferrite, right? So it's classical growth by diffusional nucleation and then growth by a diffusional mechanism, right? So what does this imply, right? The fact that the thickness, our front goes by the square root of goes by the square root of t means that it slows down, right? So you have fast growth at the beginning, slow growth as time goes on, right? And the mechanism for this is you're rejecting carbon, right? So you're piling up carbon in front of your ferrite, right? So that means you have more that you have to diffuse away to be able to, to nucleate. So that means when you have something like this, right, growth like this, do you expect pro-eutectoid ferrite grains to have a big dispersion in size, or a small, be relatively all the same size, or near the narrow size distribution? Right? What's the implications of this? Right? So think about that. Right? Even if you have grains nucleating at different times, right? Your small grains, your new grains are going to grow much faster than your larger grains. So basically, you're going to be catching up, right? Your small grains are always catching up to your bigger ones. And so you're going to have a narrow, right? So if we go back to the microstructure, here, right? And we look at these proeutectoid ferrite grains, they're fairly uniform with respect to their grain size, right? They're not super large or small, right? Okay, massive ferrite, right? No partitioning occurs by massive transformation. It's all just single atomic jumps across the interface. No partitioning in carbon, so that means if you have significant carbon, you're not going to have massive ferrite formation, right? Only going to happen in low concentration, and because it is simple atomic jumps, what's its growth rate going to be proportional to? Diffusivity in time, right? So it's going to just be, instead of square root dt, it's just going to be proportional to dt, right? So the growth rate is going to be constant, right? Or sort of interface controlled growth, right? Because the larger your interface, the more chances you have to jump across. Okay. Okay. So then Widmanstätten ferrite, right, comes in from the grain boundary, right? We can think about primary Widmanstätten or secondary Widmanstätten, depending on whether we're growing from a prior austenite grain boundary directly, or whether we're growing from existing allotropomorphic ferrite, right? Remember, this is a displacive. This was the first displacive mechanism that we talked about. So there's a shear associated with it. And unlike Bainite, which, right, so we need to accommodate this shear. Bainite did it by slip in the austenite. Martensite does it by either slipping or twinning in the Martensite, right, because we need of our PTMT. Widmanstätten accommodates the invariant plane strain typically by having two variants grow together, right, that have opposing directions of the strain. So we minimize our energy that way, right? Carbon does distribute, right? And we think about the partitioning, right? So we've got an anisotropy between the sides of the plates and the tip. The tip we're growing into fresh austenite, right? Whereas the sides to grow, we're going to need to partition carbon out, right? And so we need to think about what the interfaces are. The sides are going to be coherent, low energy interfaces and fairly immobile, right? The boundary at the other end is the tip is, right? I've got two coherent interfaces and then I got some rounded thing joining them. So that's going to be a general incoherent interface, which has significantly more mobility than the sides, right? And that, so the lateral growth, right, happens by these ledge mechanisms, right, where we've got the coherent regions separated by these incoherent steps, which can move, right? And so we grow by the extension of these ledges. That's how we do the lateral growth, right? And we see that in the thickening. If you monitor a single ferrite plate with time, right, you see these sort of bursts as the individual ledges go across, right? Okay. So that's reconstructive ferrite growth. Yeah.
So, is the only difference between Widmanstätten and allotropomorphic ferrite that Widmanstätten is displacive?
Yeah, so it's a lower temperature, right? The TTT, it's a little lower on the TTT diagram, right? And so you have less diffusion happening, right? So you've got a displacive shear, right? And we didn't talk about the exact mechanism of what that shear is, right? That's not something that I don't think it's particularly well understood, right? As I was putting the notes together for this, I realized it was something that I didn't really understand, right? It's not. I mean, the mechanism of Martensite is complicated, right? The mechanisms of twinning are complicated. The mechanisms of Bainite, no one understands, right? And then, so I was like, well, I really don't understand Widmanstätten, what the mechanism of the shear is. As I dug deeper, it's still really sort of this open question, right? There's still a lot of, despite being our most important structural class of materials, we still really don't. There's a lot about steels we still really don't understand.
So that displacive mechanism just changes the morphology, but it's still like the same composition, same everything else.
It's still like after the fact, right? It's ferrite, right? Composition's the same as the proeutectoid ferrite, right? There's still rejecting carbon, right? So all that's still happening. It's just the actual mechanism from the transformation isn't purely diffusional, right? There's also shear associated. Right. Then perlite, right? So let's remember perlite is not a thermodynamic phase, right? It's a composite of two phases. And remember our cabbage analogy, right? Which is a really, really good analogy. Right? And the growth mechanism, right? So this Pilch-Petch relationship is close to Kurzymow-Sachs. Right? This are not important to know. I'm not going to ask you questions about that. Right. What is important is we've got two primary mechanisms, right? So we've got either nucleation from a prior austenite grain boundary or a nucleation from a proeutectoid cementite layer at the grain boundary, right? And that gives us sort of an initial different morphology, right? We're going to have a different orientation relationship with the neighboring austenite grain because of that, right? The exact orientation, whether it's pitch-petch or Beryatsky, doesn't matter for this. What is important to remember is that because of maintaining the relationship between the austenite and the cementite, the ferrite and the cementite, all of these ferrite layers are going to have roughly the same orientation, and the same, the cementite are also going to have the same crystallographic orientation. Right? So everything is going to possess a common, right? And then the notion of sympathetic sideways nucleation, right? As we grow the ferrite, we're rejecting carbon to the austenite, and eventually it's going to get high enough in concentration that it nucleates a cementite layer, right? Then as we nucleate cementite, we're going to be sucking in carbon from the neighboring austenite. Eventually it's going to get low enough that we nucleate a ferrite layer, right? And so this gives us a regular space structure with a wavelength, right? And that wavelength is going to be determined by temperature, right? And the spacing gets, right, this is where I managed to confuse myself, because remember this, and was wondering why what I knew was different than what my notes were saying. All right, remember this is inverse of the spacing, right? This is reciprocal, right? So the smaller the undercooling, the larger the spacing, right? The lower the temperature, the larger the undercooling, right? We're going to have finer spacing, and that's just because of the diffusion, right? How long does it take, right? So we've got two things thermodynamically. We've got driving force for transformation, and we also have diffusion, right? And the balance between those two things, right? Can the carbon get out of the way fast enough, right? And nucleating the other phase.
Sorry, just to clear that up, since small undercooling, small spacing, or large.
Okay, so here we're at small undercoolings, right? This is reciprocal, so this is large spacing, right? It's right. I managed to confuse myself, even though I know it, right? And I put the notes together that said what I wanted it to show. When I still got up here, I looked at the graph and confused myself. That lecture, remember? So it would be easier if it was not reciprocal temperature, but the thermodynamic theory suggests that reciprocal temperature should be linear, right? That's what we get. So that's the way it's sort of always plotted.
And what did you say about the driving force?
So it's the reason for this is because of driving force for nucleation, right, which is going to be proportional to the undercooling, and diffusivity, right, which goes by square root of T, right? So when you are at low undercoolings, you have high diffusivity but low driving force to nucleate the next phase, right? When you're at larger undercoolings, you have less diffusivity and more driving force to nucleate, right? So you have to go less distance above the critical carbon or to nucleate cementite, or lower below the critical carbon to nucleate ferrite.
It's just grain growth.
It's just grain growth and nucleation, right? Just that well, you need to partition carbon, right? But that happens relatively, right? Okay. And that if we look at the rate of nucleation versus the rate of growth, right? They don't have the same relationship. So that at low temperatures, at low undercoolings, at higher temperatures, you get growth is easier than nucleation of a new perlite colony. So you get large perlite colonies that can grow to the size of several prior austenite grains, right? They can basically take over if you're at very low undercooling, so just a little bit below the eutectoid temperature. As you lower the temperature down and go to larger undercoolings, nucleation of the perlite colonies become easier, and so you have many small perlite colonies for a given austenite grain. Right? Okay. So here we have strength of perlite with respect to the undercooling. So remember, at low undercoolings, we have wider spacing. So we have lower strengths, right, because of Hall-Petch. Higher undercoolings, finer perlite structure, higher strength because we have more confinement. Right? also work hardening, right? Because of the confinement, perlite work hardens faster than ferrite. Than, right, either Widmanstatin ferrite or idiomorphic or allotromorphic or proeutectoid, right, ferrites, because of the confinement and the tortuous structure of the perlite, right? So the dislocations can't move around each other; they're forced to interact. Okay. And then we talked a little bit about normalizing heat treatments and annealing heat treatments, and we sort of covered that again in the right. Then we talked a little bit about alloy steels, and right, we'll hit this again in heat treatments, but remember the general trends. So write down on your cheat sheet. I don't expect anyone to actually memorize all the alloy, what the alloying elements do, right? That's a perfect cheat sheet thing, right? What are the main alloying elements that come up over and over again in the notes? Silicon, chromium, molybdenum, manganese, titanium, vanadium, niobium, right? Carbon and nitrogen, of course, right? What are the effect of each of these, right? Are they ferrite stabilizers? Are they austenite stabilizers? Are they carbide formers or not? Right? Because if you have that, then answering a question where that alloy, that element comes up becomes easier, right? It's really trivial then. Right? So just on your cheat sheet, make sure you write down the alloying elements, right? And what they do, right? So ferrite stabilizers decrease the eutectoid temperature because they're stabilizing. I mean, austenite stabilizers decrease the eutectoid temperature, right? Ferrite stabilizers increase the eutectoid temperature, right? Right, and the basic trends, right, as we add chromium and manganese, right? Right, you don't need to know that plot, but right, what the effect of adding a ferrite stabilizer is going to do, right? And that when we partition elements are not, the composition of the alloying elements isn't going to stay the same. The alloying elements are going to partition preferentially either to the ferrite or the cementite or the retained austenite, right? Ferrite stabilizers will tend to go to the ferrite. Austenite stabilizers end up going to either the carbide or the retained austenite, depending on whether it's a carbide former or not, or if there is retained austenite or not. Right? And basically at the well, I didn't ask any questions specifically about partitioning. I know that, but just as a, I shouldn't have said that, but as a, as a point of reference, right? You can think about the behavior of each, right? And the diffusivity of each is strongly dependent on temperature. So you reach as you cool, you reach a temperature where no more partitioning occurs, right? This shows that manganese partitions strongly above 923, 950, and when by the time you're down to 923, there's no more partitioning of that. Yeah.
How do you normally predict the amount of the TNT? It's not showing.
It's not shown on TTT diagrams. Generally, where it's going to come into play is in bainitic structures and martensitic structures, because those have a strong athermal component, right? Where you've got a bainite start and a bainite finish, right? And a Martensite start and a Martensite finish. So if you don't go all the way down to the Martensite finish temperature, right, you still have a fair amount of retained austenite, right? And then if you temper that structure, right, you'll have partition.
But you also see that in like Martensite and room temperature, right?
Yeah, yeah.
What do you mean by the each?
Well, so for some alloys, the Martensite finish temperature is below room temperature, right? That's why we mentioned that sub-zero heat treatment, right? And so in steels that are ferritic steels, pearlitic steels, right, you're not going to have retained austenite because everything is going to go to pearlite, right? Or if you're not at a high enough temperature, right, you're then going to go to Widmanstätten, or you're going to go to Bainite, right, before you, right? Right. We mention it again, time and time again, but for ferrite pearlite steels, aluminum, vanadium, titanium are strong nitride formers, right? So they pin the grain boundaries. So microalloying with these is a good way for grain refinement, right? That comes up again in the heat treatments, right? Wow, there is a lot. I'm going to have to do some more review on Friday, which means, unfortunately, Elizabeth misses the. Maybe we can chat briefly, like a couple of the key.
I'm still coming to class.
Oh, okay. Yeah, but you're taking the exam after it, right? So that means you missed the weekend. Okay. Bainite, the key ideas here is that Bainite may not go to completion, right? It's right, you get these ferrite subunits with carbides in between. For upper Bainite, for lower Bainite, you get the ferrite subunits with carbides in between and carbides inside, right? We have a Bainite start and Bainite finish temperature. Right. The difference between upper Bainite and lower Bainite, it's a displacive mechanism, so we have shear. We see it in the surface relief. But unlike Widmanstätten, where we grow two variants, we have our Bainite, and then we cause plasticity in the austenite next to it. So we have a high, the ferrite regions in Bainite have very strong dislocation densities, right? And remember the right, the mechanism, we grow a subunit, right? And that subunit grows very fast. And then we diffuse the carbide out, and the carbide grows between the subunits. And because the subunit grows very fast, but then we have like the sort of overlapping, the growth of the overall sheath is much slower than the growth of the individual subunits, right? The subunits lengthen quickly, but the sheath lengthens more slowly, right? And that if we add elements that retard the growth of cementite, so elements that are not strong carbide formers like aluminum and silicon. Remember, aluminum is a strong nitride former, right? We can inhibit the diffusion of the carbon out, right? So the cementite layers are not necessarily important for the Bainite, right? They just happen, we form the Bainite, then we partition, right? Basically. And then lower Bainite, we get the carbides in the middle, right? And then the key thing to understand about all Bainite is there's a diffusion-controlled theories and there's diffusionless theories, right? And the diffusion-controlled theories basically says the growth is controlled by the movement of ledges, diffusion-controlled movement of ledges, just like the Widmanstätten, right? So basically, you can think of the diffusion model for Bainite formation is a whole bunch of tiny little Widmanstätten. Instead of growing long things, they only grow short things, right? And then carbides grow out, and basically because of this, right, we partition and we assume that the austenite then would be enriched in carbon because we partition as we grow. And so we would expect to see carbides growing from the austenite side of the grain boundary, but what we see in that lower Bainite, the carbides precipitate on the ferrite side rather than the austenite side. So that's adds a little, takes away a little evidence from the diffusion-controlled model. The diffusionless model, what we want to see is right. If we're not diffusing during the transformation, that means the carbon concentration is the same in both, right? So what we want is to see where our free energy curves, right, where our free energies are equal, right? And that's going to be where our transformation occurs. That's what we call our T0 line, right? And if we're less than this T0 line, our austenite will have a reduction in free energy by transforming. If we're to the right of the T0 line, our austenite has an increase of free energy by growing Bainite, right, which isn't going to happen. So we always have to be at compositions less than this T0 line. Right? The T0 line goes to higher carbon concentrations as you lower your temperature. So basically, we should be able to measure the carbon concentration, right, of the newly formed Bainite and see where our reaction stops, and we see that it does stop at this T0 line, and so that gives pretty good evidence for a diffusional mechanism. That's the kinetics that we talked about before, right? Acicular ferrite is basically Bainite, but instead of nucleating at a prior austenite grain boundary, it nucleates in the grain heterogeneously from dislocations or other small particles. Right? Non-metallic inclusions are a big nucleation spot, but acicular ferrite is basically just Bainite, just growing in a different way. And we see that because it also stops at the T0 concentration. Yeah.
Earlier you said you were going to point out the difference between upper and lower Bainite. Is that purely the dispersion of cementite inside the Bainite?
For the purposes of the class and the exam, yes. Right, they just have slightly different morphology, and that at upper Bainite, you're at temperatures where you have more diffusion of the carbon, faster diffusion of the carbon, and so all of the carbides form outside right between the subunits, whereas at lower Bainite it forms in. So if you get into the nitty-gritty details, right, there was a lot of work in the 70s and 80s that show that upper and lower Bainite really are two distinct, right, they behave differently, right, but there's still so much we don't understand, right, we're just, right, I don't want to add any more complexity to it, but basically that's the primary difference between upper and lower, right. Right. And that we can, tempering of Bainite, not important for the exam. And then the role of alloying elements we see with the heat treatment, right? And basically, what are bainitic steels good for, right? They're really good for cheap, medium strength steels, right? Very little easy processing, cheap alloying elements, right? Easy processing. So, okay, announcements, right? Midterm is Monday. Second exam, I guess not really midterm. Format is the same. I sort of finalized it. There's going to be 2 short answer questions, right? And they're each going to sort of have their little A, B, C, right? Like 1 sentence for each part of those, right? So it'll be a little clearer, sort of specifically the talking points on the short answer, right? So you might have to write a little bit more, but shouldn't be guessing as to sort of exactly what I'm looking for. And then there'll be again 2 longer answer, right? So I'll have the hour to do it. Yesterday, I was at a steel workshop from the Air Force on affordable munitions steel, and not being really a steel guy or doing a whole lot of research in steel, I always had this sort of niggling feeling at the back of my head that I might not be focusing on the right stuff. And it turns out that there was a whole bunch of discussion on some really key fundamental physical metallurgy stuff of steel. And I think anyone from this class, right, if you'd sort of been paying attention topically, would have been able to sit in and hold their own with the conversations that were happening, right? And this was a workshop for people from the Air Force Research Lab, Naval Research Lab, Army Research Lab, a couple universities, and basically all the major steel players and industry people. And there was a room of there was 50 of us in the room. And as we go through the review, some of the rest of the review sites, I'm going to keep pointing out a couple things that came up in conversation again and again. It made me feel really good about sort of the breadth of things that we're talking about, that key issues that came up in this class are the same things that came up in that key discussion. So Wednesday we started the review, and there were a lot of good questions, so we didn't quite get through it. So I want to go through the twinning and Martensite, and the heat treatment of steels, with sort of a special focus on the heat treatment and reviewing a couple key points that are there. As far as twinning and Martensite goes, we want to keep in mind the similarities between the two, right? We both have significant shear transformations, and in Martensite we also have a normal component. It's not just the invariant plane strain, right? But mechanically they behave a lot the same. We get these long lenticular structures, and the lenticular aspect is because of the minimization. That's the shape that helps you minimize the strain energy, and that has important consequences with the interfaces, right? And we keep going back to the analogy of diffusionless or military transformation versus civilian, or we shall overcome diffusional transformations, right? So as far as exam stuff, we're all familiar with the shear nature. What we want to keep in mind is the geometry of twinning, right? The key idea that we have if we apply a shear to this crystal, there's only two planes that are going to remain undistorted, right? The ones that are parallel to the shear force direction, those don't move, right? Those atoms just like dislocation passing by, right? They're just sheared by one step. And then there's another special plane where the angle is going to be the same before and after the shear. And just keep in mind the nomenclature, right? Our two invariant planes are K1 and K2, the twin plane and the second invariant plane. And then we want to keep our special directions in mind, our A to 1, right, which is going to be the shearing direction, and then our A to 2 direction, which is where our second invariant plane intersects our plane of shear, right? And plane of shear is orthogonal to both A to 1 and A to 2, right? So that's just the geometry, right? And we talked about the twins of the first kind and twins of the second kind, and how they affect the stereographic projections. That's not going to be critical for the exam, but we want to keep in mind what our twin system for FCC is going to be, right? And how a coherent twin interface is going to give us a defect in our stacking sequence. So what does this tell us about FCC metals that are not going to undergo deformation?
They have low stacking fault energy.
Low stacking fault energies, right? Did we ever see twins in aluminum? No, right? What's their stacking fault energy in aluminum? High, right? So 200. I just blanked on units, right? Millijoules per meter squared, right? Has to be an area. Okay, so steels, right, that undergo twinning, right, less than 40, right? So we need fairly low stacking fault energies for twinning, right? What's a key thing we spent a lot of time talking about was the mechanical effect, or the effect of twinning on the mechanical behavior, mechanical properties of FCC. And this is a really important figure. And remember, this is the reciprocal of the work hardening rate. So high slope means low work hardening, low slope means high work hardening, right? This is the figure's sort of confusing, but this is the one that was used in the reading, so I wanted to keep it so it wasn't going back and forth. Right? So the key thing on this is going from stage 2, where you have parallel twins, to stage 3, where you have intersecting twins. Right? What's the twin system for FCC? What's the twin plane?
111.
111, right? What's the slip plane?
111.
111. So in the early stages of twinning, right, is there going to be any significant interaction between the dislocations causing slip in your twin planes and your twins? No, right? They're all going to be parallel, right? You're going to have dislocations moving parallel to your twins, and then as we work harden, right, as deformation progresses, we're going to activate other twin systems and other slip systems, right? Meaning now we have intersecting twins. What does that do? What regime do we get into now? Yeah, no, I just said it, even though I didn't say it out loud.
I'll raise the marks.
Right, yeah, so, but what's the mechanism for that?
So intersecting twins will actually, right? Also that.
Hall-Petch, right? So we're we now have dislocations interacting with twins, right? We have a lot more obstacles, right? When all of a sudden now we have interfaces that's difficult for the dislocations to get across. We spent some time talking about a couple different theories for twin nucleation. Don't worry about those for the exam, right? It's still sort of this really big open area of exploration. What is important is that twinning is still, in some ways, dislocation mediated process, right? Because the lenticular shape that develops, right, means that this can't be a completely coherent interface, right? We have ledges that are coherent, right, that are offset and offsets by that are general high angle interfaces with a much higher mobility, right? And that we can grow the twins by moving the partial twinning partials that make up the grain boundary, right? So how a twin nucleates, specifically nucleates from dislocations, is not super critical, but twinning does still involve dislocation, dislocation activity, right? And that was sort of the big important bits on twinning, right? We talked about some statistics and variant selection and things like that. All right, on to the formation of Martensite, right? Remember we talked about that a fully martensitic structure is hierarchical, right? We have structure that forms, right? Packets where all the Martensite variants share the same habit plane, and then block boundaries where you have the direction, the shear direction on the habit plane, and then the individual variants where which form your subblock boundaries, which share the parallel directions in your Martensite. And then the laps, right, are the individual little Martensite subunits. Right. And we looked at the energetics. And if we look at the driving force for Martensite, right, and we take a look at iron-carbon, the free energy change, right, what do you notice? Right. Right. How big is that driving force? Right, it's huge. Right. So you can't. There's nothing you can do, for the most part, right? If you're managed to get below your Martensite start temperature, right? There's nothing that's going to counteract this big of a driving force, right? And it's interesting that very few other systems that undergo Martensitic transformations have the same change in free energy, same driving force as iron carbon and iron nickel. Right. Right. We talked about Martensite. We've got, unlike twinning, you have both a shear and a tensile component. Right. How big? What's the relative magnitude of those two? Right. What's bigger, shear or the normal component? Shear. Right. What's how for most? Let's just think plain carbon steel, right? What's the degree of, what's the amount of shear that's accommodated? Like that.
30%.
30 is sort of the total, right? So it's 20%. You get a strain of 0.2 in shear, and then in some systems up to about 0.9 in overall, right? So iron nickel, right? 20.5, right? And high carbon steels, you've got about a 9% normal component, right? And then related, right? Where is our, I thought this was closer. Okay. You know what, I will, the change in habit plane is related, but there's some other things I want to hit first. So the geometry, so the orientation relationship, right? For low carbon, we have Kurgyamov-Sachs like, right? And remember, I asked everyone to take 15 minutes, and if you're not, and just to draw out the atomic correspondence for Kurgyamov-Sachs, right? Draw the relevant planes, right? And what's the key physical notion behind this is that your close packed directions, right, remain constant, right? And so this is observed in low carbon steels. Iron nickel, we see a slightly different orientation relationship. Nishiyama-Wasserman, and then for sort of everything in between, it all gets lumped into this what's called Grenier Troiano, but that's really not a well-defined orientation relationship, right? And remember the habit plane of this changes as we increase our carbon and alloy content. We start out at 111, right? Go to 252, and then to 259 tight planes. And on the stereographic triangle, right, this is sort of the general trend of how our habit plane moves with increasing concentration. And this was a huge topic of conversation, right, is the fact that the habit plane and the orientation relationship is not constant. Generally, it's irrational, right? And we talked about the phenomenological theory of Martensite transformation as predicting. Well, predicting is not the right word. Right? Yeah, I guess predicting. That was sort of the first big success, was that it explained the irrationality, the observed irrationality of the habit plane in Martensite, right? So that's a really key big idea. We thought about mechanisms of how do we actually go from FCC to BCT, right? And first we talked about the Bain correspondence, right, where we can envision, we stick two FCC unit cells together, we have this nice BCT region. We can imagine then compressing and expanding, right? Why did we say this? There's pretty clear evidence that this is not the exact actual transformation pathway. There's no invariant plane. The Bain transformation doesn't leave you an invariant plane, right? So there's nothing in the structure of just an ideal Bain correspondence that fits the definition of a habit plane, right? And then we did some crystallography and showed that happens, and we introduced the phenomenological theory, right, which says we have three components: the Bain distortion, the shear, and then a rotation, right? So the shear gives you back your invariant plane, but it's not the result of that is that you're not, the invariant plane isn't parallel in the parent and the Martensite. So then you need a rotation to bring it back, right? And we spent a lot of time on some time on the geometry of this of the theory, and that's not important. What is important is just to sort of understand what the main components of the phenomenological theory of Martensite are, right? And what its major sort of successes are, right? And to also understand that it's in the name we say phenomenological theory, right? So what does that imply? Is it what's that? It's what we observe, right? It's not a mechanistic theory. It doesn't tell you how any of these steps happen, right? It just says that if I were to do this, these three steps, I get something that's consistent with our characterization and our observations. It's not a roadmap of how you get from here to there, right? Or what actually happens in the material, right? All right, and then we talked about two different ways of accommodating the required shear, right? You can either have slipped Martensite, just like a deck of cards, right? If you slip an average amount on each card, you're going to get a macroscopic shear. That's what you want. When do we typically observe slip Martensite? Low carbon. Right? Or we can have twin Martensite, all right, where we have either parallel regions of twins or alternating variants, right? Why do we not have just a single twin?
You need opposite shear.
Right. Yeah, so the shear that you get from the twin is not the shear that you need to maintain your habit plane, right? So we want on average, right? Okay. So the major successes were, right, it explained the existence of the rational habit planes, right? And we were able to predict the existence of the fine substructure before it was observed, right? And then, right, the hysteresis, right? Once we cool the athermal nature of Martensite and the hysteresis associated with it, right? We cool down past the Martensite start. We start transforming. We end at the Martensite finish. If we heat back up, we have to heat up higher before we start to transform. But it's athermal, right? It's not time dependent. What the heck do I mean by that? If I manage to get to the Martensite start without forming any other phases, right? If I could get down to the Martensite start quickly enough that I miss the nose on my TTT curve, does it matter how fast I cool through my Martensite region? No, right? It only matters what my temperature is, right? To a first approximation, because we then showed that some systems, right, like iron nickel, we do get a small amount of isothermal transformation that happens after. But notice the magnitude of this, right? This is 75% Martensite, and then if we hold at 223 for a couple hours, we go from 74 to 77, right? So we get 3 additional percent. But the 74% that forms, that's the athermal right off the bat, right? And we said we're not even going to try and cover the nucleation of Martensite. And growth, we know it has to be largely athermal, and it happens very quickly, and that the velocity doesn't appear to be diminished even at liquid helium temperatures, right? So it basically happens at the shear wave velocity of the material. Right. We talked a little bit about shape memory effects and pseudoelasticity, but that's not important for the exam, right? But properties, how we adjust the Martensite start and relative volume fraction of Martensite, right? Of lath Martensite versus twin Martensite, and the amount of retained alpha as a function of our carbon concentration, and as with other alloying elements, right? Right. What's the general? What's the general trend, right? If we add anything that's a Austenite stabilizer, what's it going to do?
Lower the Martensite.
Lower the Martensite start temperature, right? What's it going to do to our fraction of retained Austenite? Right? Remember, carbon is a very powerful Austenite stabilizer, right? Just like other alloying elements, right? And so that's sort of the key points on Martensite. Right. Now, in terms of heat treatment, right, this I think is a really important lecture for you guys to set of notes for you guys to go through for the exam. Right. Think about the first exam and the types of questions I asked for the long answer. Right. So the first part of the long answers was sort of about a physical, something that just was sort of rooted in physical metallurgy. I talked about the growth of nucleation and growth of GP zones, right? Then part two was all about application, right? What happens if we change heat treatment? What happens if we change alloying composition, right? So it's applying that sort of little kernel of basic physical mechanism, right? If I do the same thing with steel, right, and that's not really much of an if, right? You've seen the mock exam, right? You're going to see that it's going to follow that same trend. So where's all the application stuff? It's here, right? This is where we talked about the effect of specific alloying elements and the effects of specific heat treatments, right? Right. Make sure you know your general classifications, right? Low carbon, medium carbon, high carbon, right? What do we mean by a low alloy or high alloy steels, right? Okay. Into the big stuff, right? And it's a lot of it right up front. Again, this was a huge topic of conversation about in the workshop, because a lot of it was discussion on military's needs for low-cost, easily heat-treatable, weldable, low-alloy steels, right? So I see the welders shaking their heads, right? It's like a unicorn, right? Right. As soon as you throw the word weldable in there, right, all of your other stuff goes out the window. Okay, but if we start by thinking about what we can add into steel other than carbon, right? We can break down alloying elements as either sort of austenite stabilizers or ferrite stabilizers, right? What do the austenite stabilizers all have in common? Generally FCC, right? With the exception of copper and nitrogen, which are, right, where do they go? There are interstitials, right? So the
Carbon.
What's that?
You said copper.
Did I say copper? Carbon. Thank you. All right? Carbon and nitrogen. It's too early, right? Okay. Then there are ferrite stabilizers. All right, what do these guys all have in common? BCC or BCC-like, we'll say, right? Titanium and zirconium, right, exhibit BCC phases, but their standard phase is HCP, right? Okay, so the classes of phase diagram, I'm not going to ask anything specific about this, but this is good understanding because it basically shows the effects of the austenite and ferrite stabilizers. So how the iron-carbon phase diagram changes, particularly the austenite region with the addition of different alloying elements, right? What will come into play from a design and exam question point of view is understanding general trends, right, with respect to the eutectoid composition, right, and the eutectoid temperature, right? So what are austenite stabilizers going to do to the eutectoid temperature? Right, it says it up there, but right, lower. Why?
It's stabilized, so it's diagram longer.
Yeah. So right, we're lowering the relative free energy of the austenite phase. Okay, and so then conversely, what are ferrite stabilizers going to do? Right, raise it. Right, you're going to push the decomposition earlier. Right, and if we look at the relative effects, right? So chromium, right, is an austenite stabilizer used often more for corrosion resistance than for ferrite former, ferrite stabilizer, used more for the corrosion properties than for that. But if we just think, how much titanium are we going to need to affect the austenite phase field relative to chromium and silicon? Right? This was something we looked at specifically, right? So less than 1% titanium, right? This is the change in the austenite phase field. Less than 1% titanium basically shrinks it down, right? Where you need virtually 20% of chrome for the same same thing, right? Partitioning during the growth of ferrite. This was again something that came up repeatedly, right? But the main point of discussion actually of this workshop was in carbide forming, right? Carbide formers in alloy steels, right? Right. Why do you think that was such an important, heated topic of discussion? Okay, so that's one key aspect that carbides can do, right? They're powerful. They're very strong at pinning grain boundaries, right? Why is that an important? Strengthen. Paul Petch is one, right? What grain? What's that?
Processability.
For hot rolling. Let's sort of think just a little bit differently here, right? What grain size are we really trying to stabilize? Or
Austenite.
Austenite, right? Right. So austenite, high temperature, right? We want to maintain a fine austenite grain size at high temperatures, right? Why do we want a fine austenite grain size?
For you to phase form of the austenite grain boundary.
right? All of the reactions we talked about, for the most part, are happening at those grain boundaries, right? So if we have a finer austenite grain structure, we're going to have a much finer final microstructure, right? Right. What else? We also talked about how impact toughness is exceptionally dependent on your prior austenite grain size, right? We have impurities, right, that are going to segregate to the grain boundaries, which can potentially weaken it, right? So grain size refinement, and very importantly, the effect of getting a nice fine carbide or nitride dispersion was a real hot topic of discussion. And there was a interesting part about Air Force replacing a alloy with tungsten with one that was quite similar with that doesn't have tungsten, that has vanadium in it. Unfortunately, the exact composition, it's not publicly releasable, so I can't talk too much about it, right? But one of the key substitutions was no tungsten, a bit more vanadium, and the amount in saved both in trying to process the steel with tungsten. So you can imagine, right, tungsten's incredibly dense, right? It's not as potent a carbide former, so you need more of it. And then if you're doing a huge pour, a huge heat, say 60 tons, right? Where does that tungsten end up, right? It all sunk to the bottom, right? And they had huge homogenization issues, right? And basically by moving to a different composition, right? One without tungsten, right? And with a magic pixie dust of these increased carbide formers, they were actually able to have a penetrator steel that performed better than the tungsten, but also went from $8 a pound to $1 a pound, right? And so they were saying the total cost between processing and cost of material for some of the Air Force's large penetrating weapons was $300,000 a bomb, right? That's the real taxpayer cost savings because of the change in composition, right? So thinking about these secondary phase particles in low alloy steels is really important, right? So austenite grain size, right? We'll get back to the specific heat treatments in a bit, but your classes of TTT diagrams. So I'm not going to ask you to draw the TTT diagrams, right? But it is definitely within the realm of possibilities of being asked to interpret, right? So if we take a look at B, where we have a clear perlite bay and bainite bay, right? Versus A, where we don't have where bainite's sort of back here, right? Right? Where this is something typical of plain carbon steel, where the kinetics of the bainite formation are fairly slow, right? We have very different processing options for each of these, right? We talked about Aus forming, right, where we quench down into this metastable region here, right, our metastable austenite region, and then deform and then rapidly quench, right? Versus forming at higher temperatures, right? We also talked about austempering, where if we cool down here and then we temper, right, we can get a structure that's completely lower Bainite, right? So again, not drawing these from scratch, but being able to interpret and say, if we followed this heating curve, what are the structures that are we going to get? Be able to relate the heat treatment and thermomechanical processing back to the microstructure, right? That's what I'm going to ask you to do.
Okay.
Right. Yeah.
Would we have to identify what type of alloying elements would give us something like a separated pearlite Bainite curve?
Yeah. Well, so we didn't talk so much about that, right? Because if you look in the notes, right, I say very few steels, right? So in this case, I'd give you the composite. I'd give you this, right? Right. But leading up to that, if I give you a TTT diagram, I would sort of expect you to understand what the effect of different alloying elements, what's it going to do, right? So virtually everything is going to, no matter what you put in it, it's going to shift it to the right, right? What does that mean, right? If I shift my TTT curves to the right, right? Yeah, so you've got more time to play with, right? It means that the time for the transformations is going to be longer, right? Okay, so ferrite stabilizers, right? What are they going to do to the TTT curves? So you said depress the. So Bainite is not quite as sensitive to alloying, right, as the upper, right? Right? But what was the second part you said? Well, very little that you're going to be able to do is going to move it to the left, right? It's up and down, right? So if we, did I ask about ferrite stable or austenite stabilizer? Right? So, right, so ferrite stabilizers are going to shift the TTT curve down to lower temperatures, right? Austenite up. So think about it in terms of the same thing as from your phase diagram, right? And also austenite grain size and heterogeneity of your austenite structure, right? Finer grain size is going to shift it to the left, right? More heterogeneous is going to broaden, right? So we have the effects of microstructure. Okay. Right. I'm not going to ask necessarily about specific heat treatments. I'm not going to say, sketch the TTT diagram for austempering, right? But I might give you the TTT diagram and ask you to describe what's happening during this process and what microstructure you're likely to end up with, right? So we talked about a lot of different heat treatments, right? Austempering and patenting, right? And then we just defined all the different types of annealing, right? That's not going to be super critical, right? So it retained austenite. Right. So in alloy steels, what are the pros and cons of having retained austenite? Right. So if we have a process where we retain some austenite, we're going to have greater ductility, right? Lower distortion on cooling, right? But we're going to have decreased hardness, right? And then depending on the use case, it might cause a problem, because what's going to happen if we continue to transform to other phases while we're in service, right? Yeah, right. Especially if we are long enough, we're holding long enough at a temperature that's high enough that we're going to catch, right? Remember the tail of the TTT diagram. We hold for long enough, and we catch that lower Bainite region. We start producing Bainite in our structure, right? That could cause problems. And then another huge topic of discussion was tempering, right? And the structural changes that happen during the tempering of Martensite, right? And remember, right, so this sort of chart sort of shows the major effect, right? And so first we segregate the carbon out, and then we'll right, then it's not until stage 2, tempering at a slightly higher temperature, that we start to we'll decompose any retained austenite into bainitic ferrite. In stage 3 tempering, we start to lose the tetragonality, right? And grow mostly Widmanstätten ferrite, right? And then in tempering in stage 4, we start to spheritize our cementite, and we'll transform to equiaxed ferrite by recrystallization. So sort of know your general trends there. And then in alloy steels, by far the biggest topic of discussion yesterday was secondary hardening, and how we can encourage secondary hardening with proper alloying and heat treatment, right? So let's think back to our aluminum work here. Where else did we see a curve that looked something like this with temperature? What's that? H hardening, right? So our duplex heat treatment, right? Right. So we're growing a fine dispersion of secondary phase particles, right? Giving us an increase in hardness. Then basically this is overaging, right? This decrease here. We're coarsening our particles, and they're growing, right? So again, really, really important. And that, right, and then we sort of hit the effects of a couple different alloying elements there, right? But if we get into our actual processing, right, we can skip Martensite embrittlement for the purposes of the exam. It's just important for you guys to know that it exists. The surface hardening stuff, again, not critical for the exam. It's just more important to know that, you know, we talked about it in class, and what's actually happening there, right? You're diffusing things into the surface to get a case layer, right? But the 3 big processes for alloy steels, right? Controlled rolling, or HTMT, right? What are we doing? We're working above the A3 critical temperature, right? And we are working it so that we get recrystallization, right? We're getting grain refinement by recrystallization, and then we're pinning, right? So what do we need to pin, right? We need nice fine dispersion of particles, right? So what are our usual suspects with alloying elements that we're going to throw in there, right? What are our strong carbide formers? Right. Niobium, titanium, vanadium, and aluminum, right? Those are the guys that we want to pin our grain size, right? Or to pin our grain boundaries, right? So the same, we then talked about these same alloying elements have another effect if they're there in slightly higher quantities. They're going to, right? Controlled rolling depends on repeated dynamic recrystallization. What happens if we don't recrystallize? Right? What's our austenite grain structure going to be if we don't recrystallize?
Texture.
Texture, but more importantly, not brittle. What's the grain shape going to be? Pancakes. We've got a pancake grain structure, right? If we have a pancake grain structure, we put enough of these in to prevent recrystallization. We have pancake austenite, right? And this process then is known as hot-cold working, right? Right? They're both going to give us a very fine Martensite structure. But the hot-cold working is going to, because of the pancake grains and because of the texture, the rolling texture that develops, is going to have very strong directional anisotropy in our sheet, right? Which sometimes we may desire. And then we also talked about in the same systems, if we quench down to above the Martensite start, right? Aus forming, right? If we roll in the metastable right, austenite, and then we quench down and get our fine Martensite, right? And this gives us a, right, what's the advantage of forming in the austenite, I mean in the metastable austenite rather than above the A3 temperature? I said, so in some cases, why would we want to do this? Why would we want to form in the metastable austenite region rather than above the stable?
So you can avoid grain growth.
Right? Grain growth and coarsening of the particles. Right? You got a lot more time to work here, right? Provided the nose of the Bainite curve isn't too far forward, but we generally have enough alloying elements that we're not going to be worried about this. So again, at the workshop, there was a lot of debate about, for different steels, whether or not it would be best to process by Aus-forming route or by controlled rolling, right? So these aren't just sort of academic things I'm throwing, right? These are actual sort of people designing these steel alloys for demanding applications are still discussing, right? So that's sort of the high point for the points for the exam. I'm going to be around for anyone who has specific questions today, right? Also, definitely shoot me emails with specific questions. The one key piece of advice is, right, we covered a whirlwind tour of steels, right? This third of this semester, right? There is a ton of information there, right? the focus on the big picture things. Don't get lost in the details, right? Right. The really big picture ideas are where 95% of your points on the exam are, right? I don't care that if you get titanium and zirconium reversed in terms of their ferrite stabilizing ability, right? But what we do care about is what's the big effect of ferrite stabilizers on the phase diagram and on the TTT diagrams, right? I care about what are the main mechanisms of pearlite nucleation, bainite nucleation, and growth. I don't care about very specific details of what's happening in different alloy systems, right? Give me the big physical metallurgy picture, right? And if you keep that in mind, it reduces what you need to study by 75%, right? And also gives you pretty good indications of the types of questions that I can realistically answer and have you guys work through in an hour, right? Without having memorized the entire slide deck and reading.